Hey there, what's going on? We are going to continue going through the Rust programming language book, and today we're going to start talking about ownership. We've hit the understanding ownership section of the Rust programming language book, so let's jump in. Ownership is Rust's most unique feature and has deep implications for the rest of the language. I mean, vague, but I think fair when we'll look at all of this in context. It enables Rust to make memory-safe guarantees without needing a garbage collector. True, at least some kinds of guarantees. So it's important to understand how ownership works. Sure, you want to use the Rust programming language, you're going to have to play by its rules. In this chapter, we'll talk about ownership as well as several related features, including borrowing, slices, and how Rust lays out data in memory. All right, so what is ownership? Ownership is a set of rules that govern how a Rust program manages memory. All programs have to manage the way they use a computer's memory while running. This is a fact. There's some control at the level of the operating system, but for what the operating system has given a process, that process has to make do with it in whatever way. Not that the process itself can't ask the operating system to change things like memory allocation, but rather just to say it's not the fundamental framework. So, some languages have garbage collection that regularly looks for no longer used memory as the program runs, languages like Python and Go. In other languages, the programmer must explicitly allocate and free the memory, so languages like C and C++. Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks. If any of the rules are violated, the program won't compile. In other words, this is an attempt to move something that could be a runtime memory safety guarantee up to a compile time, or even a checker if it's not strictly compiling. And that goes back to an old principle of moving quality assurance upstream if possible, a fail-fast strategy. So none of the features of ownership will slow down your program while it's running. So yeah, this is this so-called kind of abstraction. Gosh, I'm forgetting what the term is. I'm sure we'll encounter the term, but basically a freebie. But it's of course not really a freebie. These checks will cost something at compile time. Zero cost of abstraction. The term just came back to me. But truthfully, it does cost you something, but it doesn't cost you runtime in production. So because ownership is a new concept for many programmers, it does take some time to get used to. Sure, it takes some time, although to be honest, so far I've found that the topic is pretty straightforward. Even when I went through parts of this book and other materials before, I'm curious to see what I struggle with and to learn more about what other people struggle with ownership, because it seems like a very simple set of rules, some things like, only one mutable reference and any number of immutable references and stuff like that. It doesn't really seem complicated, and so I wonder if it's the rules are hard to follow or if it's something else. So let's continue. The good news is that the more experienced you become with Rust and the rules of ownership, the ownership system, the easier you'll find it to naturally develop code that is safe and efficient. Keep at it. So this is basically saying that this is an investment, rather than saying that this is low-hanging fruit of going, hey, you don't need to know anything. This is just an instant win. This is to say, if you put in the effort, you get some benefits from this in the long run. When you understand ownership, you'll have a solid foundation for understanding the features that make Rust unique. In this chapter, you'll learn ownership by working through some examples that focus on a very common data structure, strings. Good old strings. Almost every programming language I've ever seen has strings. Not literally every, but man, strings, good old strings. Okay, so the stack and the heap. This is going to have to do with memory management. So many programming languages don't require you to think about the stack and the heap very often. So for example, in Python, I don't think the subject even really comes up because everything is managed by lower level implementation details. I kind of wonder if everything is heap allocated, but I don't know. I don't mean to say everything in the C Python interpreter is heap allocated, but just if you start specifying some user-defined data structures, I feel like because everything's mutable, it has to have some heap allocation associated with it. But anyway, We'll see. So whether a value is on the stack or the heap affects how the language behaves and why you have to make certain decisions. Parts of ownership will be described in relation to the stack and the heap later in this chapter. So here is a brief explanation in preparation. Man, I just love a bit of preamble. All right, so both the stack and the heap are parts of memory available to your code at runtime, but they are structured in different ways. The stack stores values in the order it gets them and removes the values in the opposite order, and this is often referred to as last in, first out, or LIFO. And this comes up in all kinds of like queuing systems or systems where there's some kind of network scheduler rule, and LIFO is among them. All right, so think of a stack of plates. Oh, also depth first search, if I remember correctly, uses like basically a stack, whereas breadth first, I believe, is a queue. All right, anyway, blah, blah, blah. When you add more plates, you put them on top of the pile, and when you need a plate, you take one off the top. That's a pretty good analogy. I think that's generally, or at least typically, true. Adding or removing plates from the middle of the bottom wouldn't work as well. True. Adding data is called pushing onto the stack, and removing data is called popping off of the stack. All data stored on the stack must have a known fixed size. You can't reshape it. Data with an unknown size at compile time, or a size that might change, must be stored on the heap instead. Now, the heap is less organized. When you put data on the heap, you request a certain amount of space. The memory allocator finds an empty spot in the heap that is big enough, marks it as being used, and returns a pointer, which is the address of that location in memory. This process is called allocating on the heap, and is sometimes abbreviated as just allocating. Pushing values onto the stack is not considered allocating. That's pretty good as a little piece of terminology, because I might have accidentally made that kind of mistake myself of saying allocating to the stack. But if that's not technically correct, maybe I shouldn't say that. Instead, it's pushing to the heap and then pushing to the stack and allocating to the heap. Gosh, I need more coffee. All right, so because the pointer to the heap is a known fixed size, you can store the pointer on the stack. But when you want the actual data, you must follow the pointer. So the pointer may go to the heap, right, for what it points to in memory. Think of being seated at a restaurant. When you enter the state of the number of people in your group, and the host finds an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you've been seated to find you. All right. That's fine as an analogy, I guess. So pushing to the stack is faster than allocating on the heap, because the allocator never has to search for a place to store new data. That location is always at the top of the stack. Fun facts about stacks. Comparatively, allocating space on the heap requires more work, because the allocator must find a big enough space to hold the data and then perform bookkeeping to prepare for the next allocation. So, it kind of reminds me of the knapsack problem, which is technically different in some important ways. Like, as a bunch of programs are running on the computer, of course, it's a more dynamical kind of system for what is allocated, what's available. But this idea of like the knapsack problem is you got a sack and you want to put in as many, I can't remember what it is, candy bars or whatever it is. Fill the stack as much, the sack as much as you can, the knapsack with whatever the objects are, and that kind of requires knowing that each has like a cost capacity of like searching for the right combination of things to maximize how filled the knapsack is, which is not really a dynamical problem. Like, you could generalize the knapsack problem and then it would start to look more like this memory allocation problem, but it is like a legitimate kind of math problem to go, what is the best way to allocate to the heap and or pop to the stack? What's the best way of allocating, deallocating, and all of that? I'm sure some computer scientists have delved into that. So accessing data in the heap is generally slower than accessing data on the stack, because you have to follow a pointer to get there. It has to do a search problem of some kind to find that address. Contemporary processors are faster if they jump around less in memory. Continuing the analogy, consider a server at a restaurant taking orders from many tables. It's most efficient to get all the orders at one table before moving to the next table. Taking an order from table A, then an order from table B, then one again from table A, and then one again from table B would be a much slower process. By the same token, a processor can usually do its job better if it works on the data that's close to the other data as it is on the stack rather than farther away as it can be on the heap. When your code calls a function, the values passed into the function, including potentially pointers to data on the heap, and the function's local variables get pushed onto the stack. When the function is over, those values get popped off of the stack. Nice. Keeping track of what parts of code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so that you don't run out of space are all problems that ownership, we'll say, helps address. Once you understand ownership, you won't need to think about the stack and heap very often. But knowing that the main purpose of ownership is to manage heap data can help explain why it works the way that it does. So, the ownership rules. Look at that. There's 3 of them. Not a lot of rules. First, let's take a look at the ownership rules. Keep these rules in mind as we work through the examples that illustrate them. Let's do it. So the first rule, each value in Rust has an owner. In other words, there's some kind of pointer related to it between the stack and the heap, and there can only be one owner at a time. So no sharing, which is probably where I expect a lot of people go wrong in mistakes. That's where I guess I would go wrong, but we'll find out more as we go along. When the owner goes out of scope, the value is dropped. The value will be dropped. Okay. I mean, that makes sense. You're basically done with the local variable. You normally have to get rid of it, right? And I think even a lot of other programming languages, we'll pick on Python for a second, you get to the end of a function, and it's not that things get deallocated right away, because that's actually managed by the garbage collector, but they will get marked by in terms of reference counting, to a reference count of 0, and so it's basically saying we're done with this now. Well, Rust does those checks at runtime and will automatically, in the compiled code for the simple cases that I'm sure we'll see later, that it will just simply take care of deallocating or calling the deallocation calls right away instead of waiting for a garbage collector. Okay, variable scope. Now that we're past basic Rust syntax, which, if you haven't been watching this YouTube series, it's a whole entire series of videos where we're going through the Rust book. We won't include all the fun main code in the examples, so if you're following along, make sure to put the following examples inside of a main function manually. All right, we'll do that. Not ideal. I kind of like the full copy-pastable things, even though at the same time, I also try not to just copy-paste. As a result, our examples will be a bit more concise, letting us focus on the actual details rather than boilerplate code. As a first example of ownership, we'll look at the scope of some variables. A scope is the range within a program for which an item is valid. Take the following variable. Let s blah, blah, blah. So what should we call this? I don't know. Let's go cargo new variable scope, perhaps. And let's let s be bound to the value of this string literal hello. A variable s refers to a string literal. And I'm saying that because I'm looking at the single double quotes, the double quotes on either side, and that's just some syntax that you got to know. So by this point, hopefully you know the syntax, but it's nice that they're reminding us, because maybe you jumped here first going Rust is different. I haven't read the syntax. Why is Rust different? Ownership, and here you are. All right. The variable s refers to a literal string, or a string literal, where the value of the string is hard-coded into the text of our program. The variable is valid from the point at which it's declared until the end of the current scope. So in this program I just wrote on the left-hand side here, it becomes valid right here where we defined it, and then it becomes no longer valid at the end of the scope where my cursor is, at the end of the curly brackets. Now let's look at their example here. Listing 4-1 shows a program which with comments annotating where the variable s would be valid. So they're saying here s is not valid since it hasn't been declared yet, and that's similar to our first line here when we're declaring the main function, that first line. S has not been declared yet, then s is declared, so s is valid from this point forward, and then do stuff with s, and then by the time we reach that closing bracket, s is no longer valid. So, in other words, there are two important points in time here. When S comes into scope, it is valid. It remains valid until it goes out of scope. At this point, the relationship between scopes and when variables are valid is similar to that in other programming languages. Now we will build on top of this understanding by introducing the string type. So again, if you're going, wait, what's the difference between a string and a string literal? I suggest looking at the data types. We should go on out, I suppose. Sure. All right. To illustrate the rules of ownership, we need a data type that is more complex than those we covered in data type section chapter 3. The types covered previously are of known size, can be stored on the stack and popped off the stack when their scope is over, and can be quickly and trivially copied to make a new independent instance if another part of code is needed to use the same value in a different scope. But when we want to look at data that is stored on the heap and explore how Rust knows when to clean up that data, and the string type is a great example. Okay, we'll concentrate on the parts of string that relate to ownership. These aspects also apply to other complex data types, whether they are provided by the standard library or created by you. We'll discuss non-ownership aspects of strings in chapter 8. We've already seen string literals, where a string literal or string value is hard-coded into our program. String literals are convenient, but they aren't suitable for every situation in which we may want to use text. One reason is that they are immutable. Another is that not every string can be known when we write our code. For example, what if we want to take user input and store it? It is for these situations that Rust has a string type. This type manages data allocated on the heap, and as such is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using the from function like so. So I think this is actually one of the things that's a little bit weird about Rust. Maybe it's not weird in the context of all programming languages, but coming from mostly Python, I'd say it does strike me as a curiosity that if I want this string type, I actually have to do like an extra kind of method. So let s be bound to the value of, and we'll take this string, and it has this constructor kind of method thing, and we will go hello. So we're passing in a string literal to get a string. The double colon operator allows us to namespace that particular from function from under string rather than using some sort of name like string from, which is great. So, okay, that's doc strings for the string. There's no information on my LSP for the double colon, but we'll take the documentation's word for it. We'll discuss this syntax more in methods in the methods section of chapter 5, and when we talk about namespacing with modules in paths for referring to an item in the module tree. Sure. So there's a lot of promises right now of reading stuff elsewhere later. That's okay. This string, this kind of string can be mutated. In other words, we can change strings. But to do that, we have to include a mute keyword. And then let's suppose that I want to add some characters to it. I can go s, and there's a method, push string, or at least like a method, depending on how you want to think about the object-oriented stuff, which I think we'll cover later in the book. We can go, here's a push string with a comma, space, world. So you can probably see that we're setting up a hello world kind of script, but in a obviously less direct fashion. So we can go print line macro, and let's put s right inside. All right, so we've typed out that code example. So what's the difference here? Why can string be mutated but string literals cannot? The difference is how these two types deal with memory. Sure, so if I remember right, strings are heap allocated. My recollection, which they may correct me on, is that string literals are stack allocated. So if now let's just check out the behavior here. It should just print hello world if we did this right. There's our hello world. We just pushed this string, comma, space, world to hello, and then we printed it. All right, pretty straightforward as an example, I think. Memory and allocation. In the case of a string literal, we know the contents at compile time. So the text is hard-coded directly into the file executable. This is why string literals are fast and efficient. But these properties only come from the string literal's immutability. Unfortunately, we can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time and whose size might change while running the program. I mean, if you could mathematically, logically, and with other context prove, demonstrate that there was going to be some fixed maximum size, then maybe you could do something where you've got like variable size, but what's actually contained is padded or something. But then you have the immutability part, at least as far as how Rust is implemented. Okay. So where were we? Unfortunately, we can't blah, blah, blah. Sure. So with the string type, in order to support a mutable, growable, or shrinkable piece of text, we need to allocate an amount of memory on the heap, unknown at compile time, to hold the contents. This means the memory must be requested from the memory allocator at runtime. Sure. And that is, we need to figure out where to put things at runtime. And we need a way of returning this memory to the allocator when we're done with our string. Also true, you have to manage this memory for the full life cycle of that piece of data. This first part is done by us. When we call string from, its implementation requests the memory it needs. This is pretty much universal in programming languages. Sure, I agree. However, the second part is different. In languages with a garbage collector, GC, the GC keeps track of and cleans up memory that isn't being used anymore. And we don't need to think about it in most languages without a GC. It's our responsibility to identify when memory is no longer being used and to call code to be freed explicitly, just as we did to request it in the first place. Doing this correctly has historically been a difficult programming problem. If we forget, we'll waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, that's a bug too. We need to pair exactly one allocate with exactly one free. We got to put it on, we got to take it off. Rust takes a different path. The memory is allocated. The memory is automatically returned once the variable that it owns goes out of scope. Here's a version of our scope example from listing 4-1 using a string instead of a string literal. So what section? We'll just call this new memory allocation. So what do we got here? They want to show us an example where we say let s be bound to the value of string from this string literal. Now, of course, they just did a bunch of talking about, like, what if the string actually came from outside the program, but they're not actually showing us how to load strings that way, either from standard input or user input, or even for that matter from, like files or from internet connections, other kinds of inter-process communication and whatnot. But that's okay. They're basically trying to show, here's a string, and then we do stuff. And actually, to be faithful to their example, it's not just in the main function. You can actually do this within a scope like this, like a custom designed scope. And then we'd say, do stuff here. And if memory serves, you could even, although I'm going to get, I think, an error because I didn't define what this is. I mean, you could do let, bar be bound to the value of whatever this is. I'm getting errors because I haven't done all of the bells and whistles here that you need to do, including putting a semicolon here. But you could actually have foo become the value of bar, which could be something like, let's do s push string and go back to our, I guess, world example. Sure. Rust Analyzer cannot do something. What can it not do? It's an immutable variable. Isn't Rust very helpful? I mean, it does tell you a lot of these things that you're doing wrong, which, if you don't like to get feedback and improve, then you might find this kind of annoying. But anyway, let's see. Did it do all the things we wanted? We actually can't tell because we didn't really print anything, but we didn't get an error, so that's a first sign, a necessary but insufficient condition. let's print. Actually, we should just be able to put bar because it's one of these primitive types. We don't have to do any kind of special debug stuff. But we do need a semicolon, and we cannot be formatted by default because I did not return this. Required by the formatter parameter. Oh, it is a... Wait, I just made a pretty obvious blunder here, which is I kind of just assumed that I don't need to deal with formatting, but actually I do. Colon question mark. It's not return, is it? That would return out of unreachable statement because I'm returning from the function. I think you do need some formatting thing. I just don't remember what it is. Let's take a look at the documentation. Rust print string. Print shouldn't have a problem. Except what type does it think that this is? It does think that it's the unit type, so I'm not actually correctly getting that out. Fix our mistake here. What am I saying? My mistake. It's just printing a unit type. It's not actually giving back that value, which I think is interesting. Oh, well, that's because that's not S itself. There we go. So I had a good idea of something to show you, but then I kind of forgot some things about basic Rust, so we had to go figure it out. So I'll tell you what just happened is that I was blundering around thinking, you know, this will just give back the result of S push string, but this is actually just a statement that is manipulating an existing variable, but to actually return this variable into bar, which is what I was actually trying to show you, that you need to actually give S back. And yes, because it's a string and not a string literal, I think you need to also, let's just double check, make sure I don't tell you something wrong. Okay, I tell a lie. You don't have to do extra special formatting for strings. It's got you covered. All right, which makes sense. Okay, with all of that out of the way, I think all I wanted to say here is that you can use these scopes to grab variables out of them. It's almost like having a function where you can say, it's like a throwaway function, this kind of local scope. You can use it, abuse it, and then give back only what you wanted. All right, so let's get out of troubleshooting mode and causing myself trouble mode. Go back to reading the book. All right, let's read the book. It's a more reliable source of information on Rust at this moment. So this is a natural point at which we can return the memory our string needs to the allocator. When S goes out of scope, when a variable goes out of scope, Rust calls a special function for us. This function is called drop, and it's where the author of string can put the code to return memory, the memory. Rust calls drop automatically at the closing curly bracket. Okay. I don't think we want to go into depth here, but let's quickly read. So it executes the destructor for this type. This method is called implicitly when the value goes out of scope and cannot be called explicitly. This is a compiler error, compiler error 40. And however, you can take the mem drop function in the prelude, and it can be used to call the argument's drop implementation. So you can kind of customize how some data structures are dropped and consequently how they're deallocated, I would guess. But this is not a thing that you're supposed to be able to just do willy-nilly. So it is not allowed to manually call destructors in Rust. Erroneous example, you got a struct and you write an impl for a drop for foo, which is our foo struct here, and you implement the details of the implementation for drop. You give a mutable reference to self, and you print line macro kaboom. You call in the main, let foo be an instance of, let x be an instance of foo, and then you go x.drop. You'll get an error. Let's check it out. You get this error. Explicit use of the drop destructor. It is unnecessary to do this since drop is called automatically whenever a value goes out of scope. However, if you need to drop a value by hand, you can go to the standard mem drop function. So this is valid, interestingly enough. You can go struct foo impl drop for foo, and put your implementation of drop that takes immutable reference to self and prints line macro kaboom. Let mute x inside of your main function be an initialization binding to the value of an initialized foo, and then go drop x. Okay, and that should print kaboom, right? I would imagine. Kaboom. All right, you can implement this if you want. I'm not sure it's a good idea for getting started with Rust, but there it is. So, note, in C++, this pattern of deallocating resources at the end of an item's lifetime is sometimes called resource acquisition is initialization, or RAI. Or RAII. I think it's just pronounced RAI, is how I've heard people talk about it. The drop function in Rust will be familiar to you if you've used RAI patterns. This pattern has a profound impact on the way that Rust code is written. It may seem simple right now, but the behavior of code can be unexpected in more complicated situations when you want to have multiple variables use the data we've allocated on the heap. Let's explore some of those situations now. So the first one is variables and data interacting with move. So we'll just keep working in this file. I don't want to keep making new Rust projects for every example. So let's say we've got let x is bound to the value of 5, and then we have let y is bound to the value of whatever x is. And we get this unused variable warning, but that's not itself an issue, I don't think. So we can go cargo run. We do get a memory allocation error. So let's see what it's telling us. We've got compiling, memory and allocation is the thing, warning, unused variable, that's fine. Well, that is just a warning. Warning, finish dev. No, it's actually fine. It's just lots of red text, and I was like, oh gosh, it's wrong. But it's actually just pointing out that this variable was unused. There's no problem here with this assignment. So we can probably guess what this is doing. Bind the value 5 to x, then make a copy of the value in x and bind it to y. We now have two variables, x and y, both equal 5. This is indeed what is happening, because integers are simple values with a known fixed size, and these two 5 values are pushed onto the stack. So that's kind of interesting because, you know, being stack allocated as just a fixed integer value, it sounds like it's actually just going to have two copies of this on the stack. It doesn't like cleverly try to do some pointer magic. Well, it'll be some pointer magic, I suppose, but it's not the same. It's actually just creating two values of 5 that can be found with these names. So that's interesting. And also note that this is not really a problem for any kind of assignment, partly because these are both immutable. They're not mutable types, so no problem with, even if we wanted to add, there shouldn't be a problem with us adding another reference to x here, for example. But if this was mutable, that should be a problem, right? Variable does not need to be mutated. Fine. I think, oh, but I'm shadowing. Okay, that's another thing. Maybe we'll get to shadowing later. But anyways, you can't have multiple references to a mutable thing. And here I'm accidentally just overshadowing something. So get rid of that. All right, let's look at the string version of that. So now we're going to go from these integer literals to strings. And as we talked about, strings are heap allocated, not stack. I guess I wanted to say allocated, but we'll say on the stack? Stack pushed? I don't know. I actually don't mind the term allocation to heap, but maybe I'm wrong about the terminology. Okay, so we get this unused warning, and we get this assignment that whatever S2 is bound to is whatever the value of S1 is. And here we get some warnings, which we saw due to the LSP, the Rust analyzer anyway. No problem. And it does make some rule about, you know, like if you have an unused variable, you could prefix it. And that will tell the cargo analyzer that it's fine. Okay, this looks very similar, so we might assume that the way it works would be the same as how it worked up here. But that is, the second line would make a copy of the value in S1 and bind it to S2, but this isn't quite what happens. Instead, we're going to do some pointer magic. So take a look at figure 4-1 to see what is happening to string under the covers. A string is made up of 3 parts, shown on the left, a pointer to the memory that holds the contents of the string. This is your stack here with the index and value, and this group of data is stored on the stack. On the right is the memory on the heap. Oh, did I get that wrong? A string is made up of 3 parts, as shown on the left. A pointer on the memory that holds the contents of the string. Yes, this is the pointer. That's fine here. A length, that's here, the length 5, and a capacity, right? That's 5. That says the length of this. And then over on the heap here, we have the actual contents. So figure 4-1, the representation in memory of a string holding the value hello bound to S1. Sure. The length is how much memory? In bytes, the contents of the string are currently using. The capacity is the total amount of memory in bytes that the string has received from the allocator, which are not necessarily the same in general, but in this case they are. The difference between length and capacity matters, but not in this context, so for now it's fine to ignore the capacity. When we assign S1 to S2, the string data is copied, meaning we copy the pointer, the length, and the capacity that are on the stack. And here's the really important clincher difference between this and the example with the integers. We do not copy the data on the heap that the pointer refers to. In other words, the data representation in memory looks like 4-2. We have S1, which this variable basically comes with a pointer that points to this index in memory. The length, which is 5, the capacity is 5. So this pointer describes this data, but this pointer related to the S2 variable also points to this data. Here's our pointer, and then we have the length, and that says it's got a length of 5. And then we have this capacity, which is also 5 in this context. So this representation does not look like 4-3, which is what memory would look like if Rust instead copied the heap data as well. If Rust did this, the operation S2 bound to the value of S1 could be very expensive in terms of runtime performance if the data on the heap were large. In other words, you would get this kind of duplication. And that is a cost of the stack, but the stack is kind of meant for special cases where it's already kind of efficient to just copy. All right, so earlier we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the memory for that variable. But figure 4-2 shows data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they will both try to free the same memory. This is known as a double free error and is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. Okay, so you've said that something is deallocated twice, has some kind of security context, security vulnerability related to it. To ensure that memory safety after the line let S2 be bound to the value of S1, Rust considers S1 as no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Check what happens when you try to use S1 after S2 is created. It won't work. So, okay, before we write out the code, which will probably give us the error, and before we read the error down there carefully, we got let S1 be bound to the value of string from hello. We've seen that before. And then we're going to go let S2 be bound to the value of S1. And then if we try to call print line macro, we're going to get this error because of ownership. Okay, let's take a look. Let S1 be bound to the value of string from hello, and then let S2 be bound to the value of S1, and we will then, there's no error so far, but when we try to use the print line macro, we're going to get this error because of ownership rules. World. We get borrow moved value here after move. All right. And if we run it, we'll get this error, and we'll get some complaints about the value borrowed here after we moved. This is what's called the move in the original assignment, move S1 because S, let's read the thing here. Let's try again, get that into a more readable format. So we get compiling memory, blah, blah, blah. We get the first error with let, oh, this is just saying it's not used, that's fine. Borrowed move value S1. Move occurs because S1 has type string, which does not implement the copy trait. Let S2 be bound to the value of S1. We'll talk about copying later, but it's basically what if you do actually want a copy? Obviously, that's what the name kind of suggests. Whereas Rust by default is not going to copy these things. So print line macro, the value borrowed here after move. Note this error originates in the macro create format args_nl, which at least I don't know what that is, which comes from the expansion of the macro print line with some stuff about macro nightly builds. That's fine. Consider cloning the value if the performance cost is acceptable. That's like an easy thing, but it's not necessarily the best advice here. You could clone, but it depends what you want this for. But anyway, that's our first example of getting a memory error, where I could see somebody opening up Rust and going, like I just want to make this string, and then I copy this, and then I print like the first one. Why is it broken? What if I do the second one? Oops, I don't want to record a macro right now. Go run, hello world, no problem. All right, and that's because I'm doing something called shadowing here. All right, we'll get to that. So you'll get an error like this because Rust prevents you from using the invalidated reference. This is the error that we skimmed over. I guess we could, take a quick look at Rust C -- explain E0 382. And they've got this little example with a struct where they they define a struct that takes a value S that will be of type U32. And then we've got an initialization of it of let mute X RC new, ref cell new, my struct, reference cells. I don't know about this yet. We'll have to learn what this is, which is not a very beginner-friendly example. If you're thinking about this chapter of the book, it hasn't told us what a ref cell is. So not great, but let's go let y be bound to the value of x.clone. So we're making a copy of x, and then we go x.borrow, mutable borrow dot s is bound to the value of 6. Print line macro. With this approach, x and y share ownership of the data via RC reference count type. Reference counts, I see. Reference cell essentially performs runtime borrow checking, ensuring that at most one writer or multiple readers can access the data at any one time. So this is starting to sound a lot more like some runtime kind of checks. Maybe this is even how stuff is actually implemented when the compiler is deciding what to compile. I don't know. If you wish to learn more about ownership in Rust, that's the chapter we're reading right now, so no problem, we'll just continue. If you've heard the terms shallow copy and deep copy while working with other languages, the concept of copying the pointer length and capacity without copying the data probably sounds like making a shallow copy. It absolutely does, and this happens all the time with Python. And that kind of problem is usually for, like, you've got a more nested, complicated structure that has lots of references that expand out, and that a kind of deep copy copies everything, the data. A shallow copy would copy only the references, and then there's also just variable reassignment in Python as well. So, but because Rust also invalidates the first variable, instead of being called shallow copy, it's known as a move. In this example, we would say that S1 was moved into S2. Actually, I tell a lie, this is not shadowing. Shadowing would be if I let S1 be something else, that I'm taking S1 and I'm replacing its value with something else. That's shadowing. This is moving, to follow the correct terminology. Thanks for being confused with me. All right, so S1 and S2. So S1, we got this pointer that goes to the heap, and S2, it's got the pointer that also goes to the same place in the heap. That solves our problem. With only S2 being valid, when it goes out of scope, it alone will free the memory, and we're done. So there's a kind of partial ordering that is implied by the instruction order that we write into our code for how things will be deallocated within a given scope. In addition, there's a design choice that's implied by this. Rust will never automatically create deep copies of your data, which maybe sometimes is bad, but frankly, it's often pretty good to not just make lots of copies by default. Therefore, any automatic copying will be assumed to be inexpensive in terms of runtime performance. I like it. Scope and assignment. The inverse of this is true for the relationship between scoping, ownership, and memory being freed via the drop function as well. When you assign a completely new value to an existing variable, Rust will call drop and free the original value's memory immediately. Consider this code, for example. All right, let's type it out as we go along. Let's make a mutable variable string that's bound to the value from. Should look pretty familiar at this point. We got S is our string. And we're going to go string from ahoy. Okay, we're getting all kind of piratey about this. And then we can go print line macro. And we might predict, like, what is this going to say? What do we predict that this will say? What is my prediction? We're first creating this S, but I think this might be actually shadowing here. We're going to actually replace S, and the name S is mutable. We can change what it is, including just completely replacing it with something else. And so my prediction is that it's going to say ahoy world rather than hello world. Ahoy world. Okay. We initially declare a variable S and bind it to a string with the value hello. Then we immediately create a new string with the value ahoy and assigned it to S. At this point, nothing is referring to the original value on the heap at all. Figure 4-5 illustrates the stack and heap data now. That is, by the time you've gotten to this instruction, what does stuff look like? You got S, and it now points to the 0 index at ahoy. And what can I say about that? Length 4? Sure. It now has a length of 4, but notice that before it had 1, 2, 3, 4, 5. And capacity 5. So that's changed as well. The properties for the length and the capacity for that variable can change when it's a mutable variable, not just the data contents. So that would be awkward otherwise if you started with something that had a length of 5 and you can mutate it, but you could only like mutate it to other things of length 5. That would be kind of restrictive, I would say. Okay. The original string thus immediately goes out of scope. Rust will run the drop function on it, and its memory will be freed right away. When we print the value at the end, it will be ahoy world. So at this point, where we define S is bound to the value of string from ahoy, we are at that time going to deallocate the heap memory associated with this hello. Even though some of the other data for the S is just changing, like the where the pointer goes, what the length is, and what the capacity is, but this name S remains the same. Variables and data interacting with clone. If we do want to deeply clone the heap data of the string, not just the stack data, we can use a common method called clone. Kind of makes sense. We'll discuss method method syntax in chapter 5, but because methods are a common feature in many programming languages, you've probably seen them before. Here's an example of the clone method in action. All right, let's take a look at this. Maybe we'll just keep that part. And we'll go let, and actually we don't need this to be mutable anymore. We're going to stick to some immutables. And this is S2, that's S1. We'll bind this to the value of S1.clone. And here we're making a copy, a heap copy on the heap. Cusco's poison, poison for Cusco. All right, so we got S1, and we'll print formatted S1 and S2. It's equal to the formatted S2. Close that with a semicolon, and we will go cargo run. So S1 is bound to the value of S2. S2 is bound to the value of hello. All right, that shouldn't be surprising. We just copied. Copying should preserve the properties, right? So this works just fine and explicitly produces the behavior shown in figure 4-3, where the heap data just does get copied. Remember, 4-3 was this one, where we have basically S1 in parallel exists with S2. Make a full copy, not just the pointers, the capacity, the length, but also the content is copied. So then we can also do, for stack-only data, copy. So this is a thing where it's a matter of terminology, and I myself am going to have to get used to this because I'm kind of a little bit sloppy. Like clone, copy, they kind of seem like they're the same. But what they're intimating here is that copy is for stack, and that clone is for heap. All right, so let's, there's another wrinkle we haven't talked about yet. This code using integers. Part of what was shown in listing 4-2 works and is valid. So if I say x is bound to the value of, 5, and we say, I got to do let y be bound to the value of x, and then let's replace some things here for our names. X, we got y, and we got y. Let's do it again. So we get that printed out. That's all very nice, and it all is implicitly copied. We didn't have to call clone. It's copied automatically. But the code seems to contradict what we just learned. We don't have to call clone, but x is still valid and wasn't moved into y. The reason is that types such as integers that have known size at compile time are stored entirely on the stack, so copies of the actual values are quick to make. That means there's no reason why we would want to prevent x from being valid after we create the variable y. In other words, there's no difference between deep and shallow copying here, so calling clone wouldn't do anything different from the usual shallow copying, and we can leave it out. Rust has a special annotation called the copy trait that we can place on types that are stored on the stack as integers are. We'll talk more about traits in chapter 10. So we don't know what a trait yet is so far as what we've read in the book, but I have seen them. They're very cool. They're kind of like sharing some kinds of functionality or API surfaces for objects kind of thing. They kind of are like mix-ins. So if a type implements the copy trait, variables that use it do not move, but rather are trivially copied, making them still valid after assignment to another variable. Rust won't let us annotate a type with copy if the type or any of its parts are implemented with the drop trait, because the drop is all about heap deallocation. If the type needs something special to happen when the value goes out of scope, we can add the copy annotation to that type. We'll get a compile time error. We've created a contradiction. To learn about how to add the copy annotation to your type to implement the trait, see derived traits in Appendix C. I don't think we need to do that at some point if we want to, hopefully we'll read most, if not the entirety of this book. Hopefully we'll get to talking about derived traits in Appendix C, in which case we can talk about this subject of what if I do want to have the copy trait. So what types implement the copy trait? You can check the documentation for the given type to be sure, but as a general rule, any group or of simple scalar values can implement copy, and nothing that requires allocation or is some form of resource can implement copy. Here are some of the types that implement copy. So all integer types, such as U32, the Boolean types, true and false, all the floating point types, such as F32 and F64, the character type, char, char, whatever, Charzard, tuples, if they only contain types that also implement copy. For example, a tuple with I32s for its signature implements copy, but an I32 with the second position being string does not. Sweet. Ownership and functions. I wonder if arrays implement copy. That's not on this list. Arrays have to have all the same type, but I guess they don't have to always contain stuff that implements copy inside of them. Is that right? Uniform types, homogeneous types. Interesting. Interesting it's not on the list. Okay, so ownership and functions. The mechanics of passing a value to a function are similar to those when assigning a value to a variable. Passing a variable to a function will move or copy, just as assignment does. Listing 4-3 has an example with some annotations showing where variables go into and out of scope. Finally, a little bit more typing. Let's go through it. I'm almost excited for it. Got to practice that typing of code boilerplate. Let's go from hello. And then we've got some hypothetical function, I guess. Yeah, this, oh, they're defining the functions down below. That's valid. Okay, ownership takes ownership. Yes. Currently undefined, but we will define that momentarily, not to worry. And then we'll go let, what they want to go with. X is bound to the value of 5. And then we can call this other function makes copy on X. We got to define these functions or we'll be in trouble. So let's go fun takes ownership. And what do we got? Somebody once told me string. And we'll just put a print line macro some string. All right. Does it need to have a return type here? It does not, apparently. Some strings come into scope. Here are some strings to go out of scope and drop is called. The backing is memory is freed. Sure. Okay, let's define the other functions. We got fun makes copy some integer I32 print line macro, and we can go interesting. Is this pretty much the same function? Some integer. Oh, the difference is the types though. The string versus the integer. Oh, I got some sting here. Some sting. Got a little bit of like early one morning with time to kill. Borrowed Jim's rifle and stood on the hill or something. Okay, anyway. All right, let's grab cargo run. So we ran it and it prints hello world. And it's also going to print 5 here when we go to makes copy. So takes ownership. That matter. Why that's happening here for these two is because this is about heap allocated data, strings, but here is about integers, which are stack allocated. All right. If we tried to use s after the call to takes ownership, Rust would throw a compile time error. Let me see. If we tried to use s after the call, yes. Okay, so if I said like let's s push string, which is theoretically a valid operation, and we wanted to push, I don't know, foo, we're going to get this cannot mutate immutable. But even if I went mute s, I'm still going to get this borrow error because I've basically taken ownership. All right. Okie dokie. So try adding code to main that uses s and x to see where you can use them and where the ownership rules prevent you from doing so. I don't know exactly which things we should do. I mean, we kind of just tried out one. Let's see. I mean, if I put something similar, like I do x, let's say plus equals another 10, cannot assign twice to an immutable. That's fine. What about let x equals 10? There we go. I mean, it's complaining that it's not used, but Rust doesn't actually seem to have any problem with just reassigning this value. No problemo. All right. Return values and scope. Returning values can also transfer ownership, which I think was something I was trying to show earlier with the scope. We'll see. I think they're going to maybe do it with functions, which is fine. But you can create other kind of local scopes. All right, let's do it. Let's delete all of that. Let s1 be bound to the value of gives ownership. And actually, it's going to kind of drive me nuts with all the errors, so I'm just going to write the functions out first. Gives ownership. We're going to create a string. Notice that this function actually doesn't take any parameters, but that doesn't prevent it from being able to return something. which is a nice simple case when you're starting to think, well, okay, things that go in, we might have to worry about, is it going to transfer ownership or not, versus things that are just going to like generate a new piece of data. And then we're going to return from some string. This is the thing about Rust. I don't know if we've talked about this earlier in the series. While you can call like return it, by default, the last expression is returned. And if there's no obvious thing like this, then you're going to get an error because it expects a string. But in a simpler case, no error here. What's actually going to be returned in this empty case is the unit type. You could write that, but nobody does because like it's not clear what you would get out of that. But right, let's put it back to string, and we will return some string. Mismatch because I put the semicolon there and I shouldn't have. Okay, fun. Takes and gives back. So we got a string. What a terrible programming name, but good for these examples, I guess. All right. So string comes into scope. They are giving a nice explanation. We should probably go through it in just a second here, but a string. We're just passing it through. It takes and it gives back. All right. Anything else? Well, we need to probably finish the declarations here. So let s2 be bound to the value, and we're going to create a new string, or sorry, from a string literal. Hello. Hello, hello. Okay, and then we'll go let s3 be bound to the value of takes and gives back, and that's also one of the things that's kind of lovely about writing the functions out first, is you're going to get some auto-complete. We'll put a semicolon at the end there, and we got to fix that curly bracket. Rust-C, this file has a delimiter issue. It contains an unclosed. No, no, that's right. String returns a string. I have done something wrong. What have I done wrong? Oh, my goodness. That semicolon I deleted broke something. Don't do that. All right, so we've got these different functions. We're just going to go through and read what their comments are. So this first thing is gives ownership as a function, moves its return value into S1. So we've given from the scope of gives ownership, and we're giving it to be whatever S1 is now bound to. In this case of S2, S2 comes into scope, and we've defined it from whatever we get out of from hello. And then we're going to give and take back, where S2 is passed into takes, and then S3 binds whatever the return of takes and gives back was, which we just really wrote an identity function. It's just going to be the same, exact same string. And then their description here is here S3 goes out of scope and is dropped, and S2 was moved, so nothing happens. S1 goes out of scope and is dropped. Great. Easy peasy, I would say. The ownership of a variable. Well, let's just actually run it. There's something that feels satisfying about running things, although I am getting some unused variable warnings that are a little annoying. Cargo, there we go. It ran. No warnings. What a great day to be alive. All right, so the ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that includes data on the heap goes out of scope, the value will be cleaned up by drop unless ownership of the data has been moved to another variable. Use it or lose it, or reuse it or reassign it or lose it, I guess. While this works, taking ownership and then returning ownership with every function is a bit tedious. What if we want to let a function use a value but not take ownership? It's quite annoying that anything we pass in also needs to be passed back if we want to use it again, in addition to any other data resulting from the body of the function that we might want to return. So like this function, I suppose we could upgrade this to like a tuple with a couple of strings and return, like a string And then, oh, it's not push because that's going to change the original string. We would have to create like a new, well, we could, I don't know, we'll take the easy, probably not the ideal way out here of cloning it and then pushing string, you know, foo or whatever. And then we would have effectively, nope, still have an error. What's going on here? Syntax expression. Probably want to define something like that. Mismatch types. Expected string. Found unit type. Something's wrong with my type, but I have to go figure that out. But anyway, the point I want to make with this is that, sure, in the current state, this is just a pass-through, but what if you wanted to actually do something else and then also be able to reuse whatever we passed in, our A string, that the way you would have to go about doing that is that, like, passing through this data so that you can use it again and returning additional stuff here, so that, yeah, it would be somewhat annoying, but you could do it. Passing a lot of data around. Okay. Rust does not let us return multiple values does let us using a tuple. Oh, I think this is pretty much the example I was trying to write, but I messed up the example somehow. Maybe I was just trying to do two things in one line or something, but let's take a look at what their example is here. It's probably simpler. So they got this function, fun calculate length s string, and we'll return string usize. Let length be bound to the value of s dot length, or len, returns the length of the string, and then I could go return s, which is the length, sorry, the string originally, and also length, which is the length we calculated. There we go. There we go. All right, and then inside of this function, my goodness, we could try using our new function, calculate length. It's a little bit of a silly function in the sense of, like, would you ever want to define this particular function? Well, no, you already have the len function. Why would you need to define, you know, this is wrapper crapper kind of code. Writing wrappers when it doesn't make things better, but it is a good pedagogical example, though, right? Because you already should know kind of what that function is about. S1. Right, returns a tuple, and then we can go print line macro the length of S2 is length, or len, period, close. The length of hello is 5, which we manually counted earlier, so that should check out. Almost done here, but this is too much ceremony and a lot of work for a concept that should be common. Luckily for us, Rust has a feature for using a value without transferring ownership, called references, which we'll get into in the next section, but just so you know for a quick of what to expect, it's going to be using these and symbols beside the variable name. That's a reference, and so it's a way of saying I just want to, like, want to kind of borrow things without actually taking complete ownership, type of thing. Anyway, we'll get into all of that. But for now, thanks for watching this video. Today I felt a little bit bumbling around. Got to have some more coffee and sleep, I think. But I hope you got some value out of this video with this vlog series going through the Rust programming book. We just finished the first little section here of talking about ownership, and the next one is about references and borrowing. So how about that? I'll catch you in the next video. Take care.